Hello everyone. Today we will discuss decision tree, a popular supervised learning algorithm. Let's start. Previously, we have already seen two supervised learning algorithms, namely linear regression and k nearest neighbor classification algorithm. We have also seen the Python implementation of both of these algorithms. The content of this lecture are as follows. We will first discuss the decision tree algorithm. It includes discussing a very popular concept called entropy. We will see one example to understand the implementation of decision tree. Finally, we will implement the same algorithm using the Python libraries. First of all, decision tree is a supervised learning algorithm. That is, it works for data having x and y pair values. Though primarily used for classification tasks, it is important to mention that they can be extended to regression tasks also. The logic of decision tree lies in their use of the significance of attributes to make decisions. It intelligently identifies which attribute, such as age in loan application, are crucial in predicting the outcome. By analyzing the importance of different features, the decision tree algorithm constructs a tree of decisions leading to the most likely outcome based on the historical data. Let's take one example. In this case, as you can see, there are 5 columns which we can say as x, and then there is this y column that we want to predict. This example shows that depending upon the conditions on a given day, can we play the ball on that day? So the answer is this, in this specific example would be either yes or it is going to be no. So based on what is the outlook on that day, what is the temperature, humidity and wind, we want to predict can we play ball on that day or no. Obviously, the first column is just the serial number and it does not affect the decision making. It turns out that if we consider that given data set, it gives us this decision tree. Why it is called decision tree? Because to make a decision, first we need to check outlook. If it is overcast, then you can play the game. It is important that when the outlook is overcast, there is no need to even check further attributes like humidity or wind or temperature. However, when outlook is sunny, we need to further check what is the value of humidity. If it is high, then you cannot play the game. If it is normal, then you can play the game. On the other side, if the outlook is rain, then you need to further check the values of the wind attribute. If it is strong, then the answer would be no, and if it is weak, then the prediction is going to be yes. Then an obvious question is how this decision tree came into picture from the given data set. It is important to note that when we said that outlook is overcast, then the answer is always going to be yes. Let's try to understand from the same data set why this is the case. As we can see in the outlook column, we have 1, 2, 3 and 4 overcast values. And when the outlook is overcast, we can check that always the answer is yes. That is, whenever the outlook is overcast, you can always play the game. There is no need to even check further attributes like temperature, humidity, and wind. But this is not the case for other values. For example, if we see these three values for the rain, then in two cases the answer is yes, and in one case the answer is no. It suggests that when the outlook is rainy, then only on the basis of this attribute we cannot make a yes or no decision. We have to further check other attributes. The same is true for outlook being sunny as well. Now, an obvious question is how we will arrange the attributes. As in our example, how we would know that outlook should come on top, we also call the root node. Then humidity should come, and so on. For that, many measures are available in the literature. One very commonly used measure is the entropy measure. Entropy measures the level of disorder or uncertainty within a data set. In the context of decision trees, it plays a crucial role in determining how a data set is split at each node. A lower entropy value means more order and less uncertainty, guiding the tree to make more informed splits. The formula of entropy is given like this: summation pi log 2 pi on the basis of all the classes. So C here represent the number of classes or labels in the data set. S is the set for which we want to calculate the entropy, and pi is the proportion or probability of elements in class I within the set S. Let's try to calculate entropy from the given formula. Let's say that a data set has overall 14 examples. Out of them, 9 are positive or yes examples, and 5 are negative or no examples. In that case, entropy can be calculated like this: the probability or portion of positive examples multiplied with log 2 the same portion with a minus sign here. Once again, with minus sign, the probability of negative example multiplied with log 2 of the negative example's probability. When we calculate that, we will see that the corresponding entropy is 0.94. Remember, the lower the entropy, the better the attribute is in classifying the data. It is also important to note that there are other measures also to create the decision tree and identifying the ordering of attributes. Other famous measures include information gain and Gini index. Let's take the same example once again, and let's try to build a decision tree out of this available data set to us mentioned in this example. The first question obviously is to identify the best attribute. That is, which attributes should come on the top. For that, we have 4 possible choices. Either outlook should come on the top, or humidity, or temperature, or the wind. For that, we will calculate the entropy of each of these attributes with respect to our target concept, which is play ball. We are representing here with T, and we will calculate the entropy for all these attributes, and we will pick the one which gives us the minimum entropy. And once again, this is the rule here. Every time we will apply the entropy measure, we will calculate entropies, and the one attribute that gives us the minimum entropy, we will consider that as the next attribute in our decision tree. Let's try to explore it further. From the data set that is given to us, let's say we want to calculate the entropy of Outlook. For that, we will see how many possible values are there in Outlook. Outlook can take three values. Either it can be sunny, it can be overcast, or it can be rain. There are total 14 rows. Out of them, if we calculate, 5 belongs to sunny, 4 belongs to overcast, and 5 belongs to rain. So a total 14 rows. Out of these 5 values, 2 are positive within sunny and 3 are negative. For Outlook being overcast, all the 4 are positive and there is no negative example. For Outlook being rainy, out of 5, 3 are positive and 2 are negative. Once we have calculated all these values, the next step is to calculate entropy for individual value within Outlook. Means we have to calculate the entropy for Outlook being sunny, Outlook being overcast, and Outlook being rain. If we do the first one, that is Outlook being sunny, the entropy can be calculated like this. So the probability of positive examples, as we can see, positives are 2. So 2 divided by 5, log 2, 2 divided by 5, because the total examples in sunny are 5 with a minus sign obviously. Then minus times the negative examples probability, which is 3 by 5, because we have 3 negative examples for the sunny case, multiplied by log 2 3 by 5. If we calculate that, then the value of this specific entropy would be 0.97. That's why we got 0.97 here. Similarly, we can calculate the entropy for overcast, it would be 0. And for the rain also, it would once again be 0.97. So the entropy of overall Outlook attribute is the weighted average of sunny, overcast, and rain. That is the portion of sunny divided by total examples, which are 14, multiplied with the entropy of sunny, 0.97, as you can see here, plus the number of examples that belong to overcast. We know they are 4, divided by first the total number of examples, which are 14, multiplied by the corresponding entropy, 0, as we can see here, plus the portion of over Outlook being rain divided by the total number of examples, multiplied by with the corresponding probability. When we calculate, it turns out that the entropy of the attribute Outlook is 0.692. Similarly, we can calculate the entropy of other attributes also, like humidity. We apply the exact same process. We identify the different values for humidity. We then check the total portion of them. We divide them into the corresponding positive and negative values. Then we calculate the corresponding entropy, as we have calculated here for humidity being high. And finally, the weighted average to give the overall entropy, which turns out to be 0.789. When we calculate the entropy in the likewise fashion for all the attributes, it turns out that Outlook gives the minimum entropy, making it the best attribute to start the decision tree, or in other words, the root of the decision tree. So Outlook comes at top for having the minimum entropy value. It might now have 3 values. Outlook can be sunny, Outlook can be overcast, and Outlook can be rain. Now the next step contains creating the partial tables for sunny, partial table for overcast, and partial tables for rain. This is the partial table for outlook being sunny. What do we mean by partial table is that out of the total 14 examples, we have separated out those rows where outlook value is sunny. And we will do further decision making for the branch outlook being sunny out of this data set only. That is, when the outlook is sunny, which further attribute we need to check? Either we need to check temperature, or we need to check humidity, or we need to check wind. For all these three attributes, we will do exact same process of entropy calculation. And the attribute which will give us the minimum entropy will be considered next after outlook being sunny. For rain also, there is a separate partial table where all the values of outlook attribute are rain. Similarly, we have calculated the partial table for overcast also. Once again, all the values here are overcast. But in this specific partial table, we can see a trend. That is, whenever the outlook is overcast, the corresponding class is yes. So, for overcast, we need now to check further attributes like temperature, humidity, or wind. We can directly make the decision that whenever the outlook is overcast, the answer is always going to be yes. That's why we have made the decision for outlook being overcast. But we cannot do the similar decision making for sunny and rain. Out of their partial tables, we have to identify the further attributes. So for sunny partial table, once again, you can see that not all of them are either yes or no, right? In that case, we have to identify for overcast being sunny, which of the attribute further gives us the minimum entropy. So we will focus on this partial table only, and we will try to calculate the entropy once again. For example, when overcast is sunny, if we calculate the entropy of temperature, we have to divide that into these three further values of temperature: hot, mild, cold. Identify how many of them are positive, how many of them are negative, calculate the entropy for all of them, and then take the weighted average. In this case, the weighted average is 0.4. Similarly, we can calculate the entropy for all the three attributes, but for the case when outlook is sunny. It turns out, as you can see, that humidity gives us the minimum value. It means after sunny, we have to put the humidity attribute. Let's see. As you can see in this tree, when outlook is sunny, the further attribute we need to check is humidity, because for sunny partial table, humidity gives us the minimum entropy. Now further, humidity might have two values, high and normal. As you can see from this table, partial table of outlook being sunny, if we focus on humidity now as the next attribute, you can easily see that whenever the humidity is high, the answer is no, and when the humidity is normal, the answer is yes. Since there is a complete division between high and normal as no and yes, we can stop that decision tree with the final decision, that is, if humidity is high after outlook being sunny, then the answer is no, otherwise it is yes. The same process we need to do is for the rain partial table also, which means we have to calculate the entropy of humidity, temperature and wind once again when the value is rain. I will not discuss the further calculations, but you can see that the next attribute in this specific case is going to be wind. The reason being that in this specific partial table, for outlook being rain, whenever the wind is weak, the corresponding answer is yes, and whenever the wind is strong, the answer is no. So there is a complete division. Therefore, the further attribute is wind, and if wind is strong, the answer is no. When it is weak, the answer is yes. So in this way, using the entropy measure, we can calculate the decision tree. Remember, at each point, we have to calculate the entropy and consider the attribute which gives us the minimum value. So the next step is now, once the training data is available, we have built our tree. Next step, as we have seen in previous cases also, we have to check the performance of the decision tree on unseen test data. And if the performance is not satisfactory, we will try other measures such as Gini index, etc. So, to conclude our discussion on decision tree, let's review on the key concepts once again. They illustrate how algorithms can simulate human-like decision processes, breaking them down into a series of simpler choices based on data. Entropy measures the level of disorder or uncertainty within a dataset. Various measures such as Gini index, entropy, and others can be applied to check the relevance of attributes. It is important to note that the choice of measure for attribute relevance significantly impacts the structure of the decision tree. Depending on the chosen criteria, the algorithm may prefer different attributes and splits, leading to the creation of a completely different tree. Random forest is a famous ensemble learning method. It builds upon the foundation of decision trees. By creating a forest of diverse decision trees and aggregating their predictions, random forest models can achieve greater accuracy and robustness than individual trees. Random forests also fall in the category of supervised learning algorithms. So this is all for today's lecture. Now we will see the Python implementation of decision trees. Let's see the implementation of decision tree using Python now. I have already mounted my drive where I have stored the dataset. Let's import the necessary libraries first. As you can see that it includes the decision tree classifier. We have taken it from the tree sublibrary of sklearn library. Others are train and test split, accuracy score, and label encoder. Let's read the data then. As you can see, this is the same data that we have discussed during the theoretical discussion of decision tree. Here we have columns like day, outlook, temperature, humidity, and wind. And the column that we want to predict is play ball. Once again, the column day here is just the serial number and it does not affect the predictions. So the next step is to drop the day column. This decision tree classifier works on numerical values. However, the original values are a string. They contain values like sunny, overcast, and rain. So we need to convert that into the corresponding integers, which represents specific values. We have seen that in earlier lectures also, we can use a label encoder to do the same. Once we run this code, for each column within the data, the textual data has been converted into a number. For example, for the Outlook attribute, 2 represents sunny, 0 represents overcast, and 1 represents rain. The same goes for other attributes also. Then we have to drop the play ball column from the independent variable set, which we represent with the value x, and we need to put the play ball values into the dependent variable, which is y. Let's run this. The next step is to split the data set into training and testing data set. For this specific example, I have taken 10% of the overall data set as the test set and the remaining as the training set. The next step is to create a decision tree classifier. Here we have taken entropy as our primary measure. We can change the measure here. We also pass a random state variable with some values. Once the model is created, we refer that with the variable decision tree, and we pass the training and x training and y training values to fit the data. Running this will create the decision tree model as well as fit the data, the training data, to be specific on this decision tree classifier. The next step is to make predictions on the training data set. For that, we will use the predict function of this classifier and pass only the x values to that. Later on, based on the values of original y values and the predicted y values of training data set, we calculate accuracy. As you can see here, the accuracy here is 1, which represents 100% accuracy. That is, each row of the data of the training data, to be specific, has been correctly predicted by our decision tree classifier. The next step includes testing the decision tree classifier on the testing data set. Let's do that. As you can see here, for testing data also, which decision tree has not seen earlier, the accuracy turns out to be 1, which means 100%. So the decision tree build is good and it can correctly predict the testing data set as well as the training data set. This is a simple demo how you can implement decision tree classifier using Python libraries.